this video we're going to talk about combinations, and you use combinations when you want to talk about groups of things. So let's say we're electing 3 officers from a club of 25 people. And your first one is going to be your president, the second one is the vice president, and your third one is your treasurer. Well, in this case, your order matters. So we're actually not using a combination in this one. We'd be using a permutation. And it's written like this, 25 permutations of 3. That's how you would put it into your calculator. And you know, we'd be using the fundamental counting principle. We'd be doing 25, 24, 23, and it would come out like that. Or you can put it into your calculator. You would put it in 25, then you would go to math, go over to PRB, which stands for probability, and come down to 2, and then you push in the 3, and it gives you the 13,800. So let's make a little note to prove how order matters. If we're drawing out names, and first we draw out Julie, and she's the president, and second we draw out Lewis, and he's the vice president, then we draw out Susie, and she's the treasurer. Then we draw again, and next time we draw out Lewis first, then Susie, then Julie. This is to show how order matters, because the order in which we draw these people changes what office they get. So now let's look down here. Now we want to form a committee of 3 people from the same club of 25 people. So this time, let's say I draw out Julie, and then Lewis, and then Susie. This time, it doesn't matter who I pull first, because it's still going to be a committee of Julie, Lewis, and Susie. Whether I draw Julie first or Susie first, it's still the same 3 people. So this is an example of a combination where order does not matter. So this time I can't use the fundamental counting principle, but I can still put it in my calculator, only this time I would put in 25. I'd still go to math and go over to probability, but this time I come down to the one that looks like this, hit it, and I put in 3, and I find out that there's 2,300 ways. Notice there's many fewer ways of doing it as a combination than a permutation, and that's because I can rearrange these same 3 people several different ways, and they're coming as chunks. And I'm saying 25 people taken 3 at a time, whereas this one I'm saying 25 people taken 3 at a time, but it's in a specific way. So that's why anytime you do the same numbers, permutation, you're going to have more choices than you will as a combination. And this, it's in objects taking R at a time. So let's do some examples, or let's talk about this a little more. When counting how many ways there are to arrange some number of items and order matters, it's permutation. When counting how many ways there are to group some number of items and order does not matter, it's a combination. So let's look at example 3. You want to choose 4 officers from 30 people. When it's an officer, order matters, so it's a permutation. So I would put in 30 permutations of 4. I'm going to find out that there's 657,720 different ways of getting officers. Now, what if I want to choose a committee of 4 people from the same 30 people? Choosing committees, order does not matter. So I'm only going to get 27,405 people. So officers, order matters. Committee, order doesn't matter. So these are some ways to help you remember when to choose a permutation versus a combination. Now, with combinations, sometimes we have restrictions. So let's talk about how you do it when there are restrictions placed on what you can choose. So there's a Young Republicans Club at the local high school that consists of 7 seniors, 9 juniors, and 5 sophomores. They want to form a 4-person committee. Remember, when you're forming a committee, the order doesn't matter, so you use a combination. How many committees are possible? So if we're just forming a committee and we can choose from anyone in the club, we'd say 21 combinations of 4. Put that in your calculator. You're going to find out there's 5,985 different combinations you can get to form your committee. Now, how many committees are possible that consist of all sophomores? So this time we're only choosing from these 5 students. So this restriction we're setting affects our whole committee. We would say 5 combinations of 4. We're choosing 4 people out of 5. There's only 5 different ways we can do it. Okay, this time, for example C, we want to make a committee and the club president must be a member. So if we look back at our boxes, one person has to be the club president. So there's only 3 spots left. So we're going to set up our combination slightly differently. Instead of 21 combinations of 4 like we did before, we're going to say 20 combinations of 3. And we're choosing that because we've already pulled out one member. We pulled out the president, which left the 20 other members, and we only have 3 committee members left to put in there because we already have one of our members in there, which is the president. So we would do 20 combinations of 3, and then at the end we go back and multiply it times 1, which is redundant, but because we already have that one person, that president is in there. But there's 1,140 ways to form a 4-person committee if the president must be one of the members. Okay, now what if we want to form a committee that must have 2 seniors and 2 juniors as part of the committee? So now we've got a restriction that applies to the whole committee. So if you look at think back to your boxes, now we have a committee where we have 7 combinations of 2 because there's 7 seniors and we want to choose 2 of them, and we've got 9 juniors and we want to choose 2. So this time we need to do 2 different math problems and multiply them together. So when we do this combination, 7 combinations of 2, we find out there's 21 different ways to choose 2 seniors. And there are 36 different ways to choose 2 juniors. If we multiply those together, we find out there are, you can barely read this, 756 ways to form a 4-person committee using 2 seniors and 2 juniors.